When you think about the solar system, what pops into your head? The sun, right? The planets, maybe the asteroid belt. But have you ever stopped to wonder where it all stops? Where's the actual line between our neighborhood and, well, everything else?
You'd think that'd be a simple question, wouldn't you? But for astronomers, man, the answer has been a moving target for over a century. And what we're learning now, it paints a picture that is so much weirder, so much more alive than we ever thought possible. For decades, the textbook answer was pretty straightforward. The Oort cloud. This idea, which goes way back to the 1950s, gave us this nice, clean picture. It's this giant, perfect sphere of icy stuff way out there surrounding us. A clear boundary. Inside, you're in the solar system. Outside, you're in interstellar space. Neat and tidy. Yeah, well, it turns out that whole neat and tidy picture, it's just wrong. The edge of our solar system isn't a crisp line drawn in the sky. It's something else entirely. Something alive.
Okay, so if it's not some simple line, then what is it? Well, what modern astronomy is telling us is that it's more like a fuzzy, constantly shifting frontier. And to really wrap our heads around it, we have to look at these four key forces that are basically locked in this epic cosmic tug of war.
So here they are, the four big players that define the sun's gravitational edge. First, you've got the classic idea of the sun's reach, its Hill sphere. Then there's the constant pull from our own Milky Way galaxy. Third is this wild idea of cosmic sandblasting from passing stars. And finally, there's what we can actually see from Earth. Let's break these down one by one.
All right, first up, the Hill sphere. The easiest way to think about this is as the sun's absolute maximum zone of influence. It's the theoretical bubble in space where, if you're inside of it, the sun's gravity is the boss. It's got a stronger grip on you than the rest of the Milky Way galaxy does.
And the scale here is it's mind-boggling. We're talking about a sphere that's 100,000 times the distance from the Earth to the sun. That's about 1.5 light years across. So in a perfect universe, that's the absolute biggest our solar system could possibly be, at least gravitationally speaking. But here's the catch. That perfect sphere, it's just a theoretical snapshot. It's an instantaneous boundary. The reality is that our solar system is moving through a pretty chaotic and busy galaxy. And that brings us right to our second big force. Yeah, that second force is the constant pull of the Milky Way itself. We call them galactic tides. And it's just like how the moon's gravity creates tides here on Earth's oceans. The immense gravity of our entire galaxy is constantly stretching and squeezing our solar system. It's a powerful, relentless force, and it completely messes up that perfect Hill sphere we just talked about. And this pull, it really works in two main ways. You've got what's called a vertical tide, which basically makes things in the outer solar system kind of bob up and down as we orbit the galaxy. And then there's the radial tide, which stretches the whole Oort cloud out, pulling it towards the galactic center. Imagine stretching a piece of chewing gum. That's kind of what the galaxy is doing to us. Okay, let's get to our third force, and this one is even more chaotic. The technical term is stochastic erosion, but honestly, a much better way to think of it is cosmic sandblasting. Our solar system isn't just sitting in empty space. It's constantly getting smacked by these little gravitational kicks from all the other stuff flying by in the galaxy. And there are really two main culprits doing the blasting here. First, you have other stars that are constantly passing by. They're not super close, but they're close enough to give the edge of our Oort cloud these small but constant gravitational nudges. Then you've got the big ones. Every few 100 million years or so, our solar system plows through a giant molecular cloud. That's not a small nudge. That's a massive shove. Both of these things are always working to strip material away from the very edge of our system. So, let's recap. We've got these three powerful forces all duking it out. The sun's gravity trying to hold on, the galaxy's pull trying to tear things away, and this cosmic sandblasting chipping away at the edges. But how do we know this is what's really happening out there? I mean, we can't see it, right? Well, that brings us to the final crucial piece of the puzzle, the evidence we can actually gather from right here at home. It's true, we can't just take a picture of the Oort cloud. It's way too faint and far away, but we can see its effects. For instance, we track the paths of long-period comets, the ones that take thousands of years to swing by the sun. And we've noticed something funny. They all seem to come from a region that just cuts off at around 50,000 astronomical units. And guess what? That's exactly where our models predict the galactic tide should be strong enough to rip them away. We also see these incredible interstellar visitors, like Oumuamua and Borisov.
These things are basically escapees from other star systems' Oort clouds, and they give us clues about how this whole process works everywhere else in the galaxy. So, when you take all 4 of these pillars and you put them together, you don't get a solid wall. You don't get a nice, neat line. You get something so much more interesting, so much more beautiful. A living, breathing boundary between our solar system and the rest of the galaxy. There's a quote from the research that just nails it. It calls the edge of our solar system a fuzzy, evolving frontier, shaped by galactic tides, stellar flybys, and continuous dynamical exchange. It's not a static place. It's a zone of constant back and forth, where some objects are being lost to the galaxy, while others are being nudged inward, back towards the sun. And this new way of thinking, it actually solves some really old puzzles. For example, astronomers have always kind of wondered, if the Oort cloud is constantly being eroded away, how do we still have this steady stream of long-period comets visiting us? Well, the answer is in that dynamic exchange. The very same forces that strip comets away are also gently nudging new ones from deeper inside the cloud, basically replenishing the supply. It's a self-sustaining system. Okay, so this whole new picture of the solar system's edge is definitely fascinating, right? But does it really matter? Does it have any practical importance for us? And the answer is a resounding yes. Understanding this frontier has some very real-world implications for us right here on planet Earth. For starters, let's talk planetary defense. I mean, the better we understand where these long-period comets come from, the better we can predict any potential impact risks down the line. It also helps us make sense of interstellar objects flying through our system. And get this, the Oort cloud might even act as a kind of shield, protecting us from some of the harshest cosmic rays. All this new knowledge is already guiding the next generation of missions, like the amazing Vera C. Rubin Observatory, which is going to start mapping this region in unbelievable detail very soon. So, the big takeaway here is that we need to throw out the old metaphor. The edge of the solar system isn't a wall. It's not a fence separating us from the rest of the universe. It's more like a gateway, an active, buzzing, dynamic interface where our little cosmic home meets the vast, wild expanse of the Milky Way. It's a frontier that is still so mysterious, a place of constant change and discovery. And it really just leaves us with this incredible, tantalizing question. What else is out there, waiting for us at the true fuzzy boundary of our cosmic home?